Alright, so we're going to talk first about a logistic function, which is a special type of function. It's used in different fields, especially in like modeling population growth. And so it has a pretty weird looking general equation, but we're going to just use it and kind of look at the properties of how it works. And so one of the things to look at is we have these two horizontal asymptotes, one over here and then one up here. And we have constraints on our property. So kind of why it's used is it stuff grows slowly, it speeds up, and then it reaches some equilibrium point, and then it starts to slow down, and we have a cap. And so often you'll look at something like a population growth in terms of resources. So there'll be lots of resources, so they'll grow really quickly, and then suddenly the population kind of reaches its stability in terms of what resources it could have and use, and so it tops off at some point there. So why do we have these values? If we look at what happens as x goes to infinity, so we have a very large value on the top. That value, if we take e, which is just a number to a large power, and 1 over that, we effectively get 0. And so we, at some point, have c over 1, which is just our value of c. So this asymptote is our value of c. That's what we approach as x gets large. We can talk about what happens as x gets really negative. It's the same idea, except our values flip. And so that's a positive value, and so that's a large number, and any number divided by a large number as x goes to infinity would be effectively 0, and that is our asymptote down here. We're going to use that idea to model data to see how things fit, but really what we're trying to do with all these things, we have a linear regression, is to minimize the difference between our data and the results of our equation. So we have some real-world data, which is not going to exactly fit an equation necessarily, but we want to use some properties of what's called a regression to have a line of best fit or a curve of best fit to our data. And so to do that, we look at what are called residuals, which is a way to talk about the difference. It's what's left over when we talk about our real data and our predicted data. And so we're trying to get those values to be very small. So we'd have to come up with an equation. And so this is a best guess right now, right? So I think, all right, if I talk about this, it could be really close to 2 times 3. 2 times 2 is 4. 5 times 2 is 10, right? 2 times 3 is 6. That's closer, but it's further away here. So we just kind of guess, and we're just going through the exercise here. So let's just go with 2 times our value and see how close that gets us to our data. And so those are our predicted values, right? And then I take the residuals, which is the actual value minus the predicted value. And so that's a 1, right? Those are my residuals. And then to deal with the difference here that I really, in this case, I missed it by 1 in both directions. I don't want those to cancel out and say that I had a difference of 0 that I was right on. I take the square of those residuals. So I square my residuals, and then I can add those up. I sum those squares, and that's my sum of squared residuals. It gives me a sense of how well I captured that data. So my sum is 47. That doesn't mean a ton unless we were to try a different model. So if we were to go back and try 3x, we'd see how close we got to it. Or something even fancier, if we plotted it and fit it without a line but with a curve. We would try to make this value as small as possible. Right? So the idea is, can another function beat that value? And probably if we were to put this into some statistical software. So if we were talking about how this works, we use the sum of squared residuals, what we just did right there, and then we look at these values of our sum of squared deviations, and we get this thing called a correlation coefficient, which gets at how closely we got to what our actual value was. And you can see here, if this went to 0, if we had no residuals, we hit it exactly, this would be a value of 1, and that would be perfect correlation. And so we'll see kind of how that works as we move forward. So if we were to just plug through this, right, we're going to get the average of the real values. So that's this y hat, y with a bar over it. Y bar, and then we have down here we have y hat with a little caret, and then we have y bar. We just plug through the values. So we have some constant value there. we're trying to figure out how to deal with these data. So we pick a value, we pick a predictive function. So in this case, we'll make it simple, 3 times x. And so we make our data, right? Our residuals are just like we did before. I square my residuals, so those are some values. Now for this one, I have to get some deviation. So I need a value, right? So I add up my actual data and get the average. And then I take y minus the average, right? And that's 16. And I'm sorry, those are my values for y minus the average. Gives me the deviation squared, and I sum those values up, right? So that's 84, that's 80. I would have my values here, 84 minus 80 over 84, and I get some r-squared value of 0.22, which is not a very good fit. Right, so I'm trying to go for 1. That's my best fit as I move forward. Alright, so if I look at those, that's not very good. If we want to get a sense of what we want this to be, we want that to be nothing, so we want this to be very close to 1. That would be perfect. And that would never happen, but we could get pretty close. These are kind of a chart of our values in terms of if we have a good predictor or not. We can see that our value of 0.22 is in this range, which means that we're not very close at all to predicting our data based on this. And another thing to think about is, our sit-up's going to be correlated with days to even start. Do we have the right value here that we're plugging in, or is there some other factor that we're not thinking about in terms of sit-ups, like how much food you ate or how much sleep you had the night before? There's different things that we could put in over here to try to find what's dependent on number of sit-ups. And then as things get complicated, we can allow a spreadsheet or a graphing calculator to calculate these values for us. It's much more simple to let the computer do the work than for us to do the work. But we have to keep in mind the overarching idea of kind of what we're doing. As we work through this, we have residuals, right? So a residual shows we want to have, if we were to plot our residuals, we don't want to see any trend in them, which means we don't want to see a pattern. If we have a pattern, that means that we're consistently missing something, and if we're consistently missing it, that means that we are not getting part of the pattern. And so we want to see scatter as we plot our residuals. We'll look at different ones in live time as we go through it, but you want really kind of just no pattern whatsoever in your residuals. If you do have a pattern, you're going to have some other part of the equation that you're missing.